Hi guys. Let's look at a subject that should help with your homework, and that is adding magnetic field vectors. So this is similar to what we did with electric fields, where we want to find the magnetic field at some point. Um, and I wanted to make sure to give you a pretty substantial example because this can be kind of tricky. Um, just keeping track of the different components, and it's made more difficult with magnetic fields just because they're at right angles to the distance displacement vector. So let's look at the simplest cases and kind of build them up, and then we'll do a problem that's kind of complicated. So I figured out, as an aside, I figured out you can put a grid in here, so hopefully that'll help a little bit with um, making neater diagrams. So the situation that I want us to consider first is consider just two wires. The wires are facing you, and there's a current of the same magnitude that's flowing at you. And in this case, you know that there would be a magnetic field that would be going around these vectors or these wires in a circle. And you could use your right hand rule to determine it would look like this. You know, it would be a circle. Um, and this wire would have something similar, so you know that there would be, a magnetic field going around in a circle like this. And the important takeaway is just that if we were looking at this in the center, you can see, actually, you know what I should do? Let me put these in different colors so we can distinguish between them. So we'll have the one on the left in blue and the one on the right in red. And the thing that I just wanted to draw your attention to is, although the currents are going in the same direction and the magnetic field lines are going in the same, they have the same orientation, they would be going counterclockwise around the wire. Because imagine, looking at your hand, your thumb is pointing towards you. That's the direction of the current. So your fingers curl around, so they tell you the direction of the magnetic field. In between them, those two wires, they're going to cancel. If you're at the exact midpoint, uh, they're gonna be zero. The B field in the middle would be zero. Um, for this, at this point. Now, we could also look at, the similar situation where what if we had the wire where one, the current is coming towards you, but in the other one, the current is going away. So just to use the notation, both of these are coming towards you. Here, one is coming towards you, one is going away. Again, if the currents are the same magnitude, you would have kind of the same situation, except now this one would be going the same, like this, but our other one would be going the other direction. So now, if you're using your right hand rule, your thumb would be pointing towards the screen, and you can see the magnetic field would be curling around this in a circle. Um, and as a result, in the middle, they're aligned. And so the magnetic field there is going to be, 2 times the magnetic field of either one. Suppose we call this one B1. If the currents are the same and the distance is the same, i.e. you're in the middle, then those would have the same magnitude. And we could find that. So we know that the magnetic field magnitude looks like, around a wire, looks like mu naught I over 2 pi r, where r is that distance. So if this was, if we called this separation distance d, then we would have, let me call this the total magnetic field. And we're talking about just the point in the middle on the line that's between them for both of these. Um, This would be, well, we would have a factor of 2 because we have 2 of these factors, or 2 contributions. And then this would be mu naught I over 2 pi d over 2. And you can see, we could cancel these factors of 2 or whatever. The total magnetic field in the middle would be 2 mu naught I over pi d. And if we were being careful about this, we would note that this would be in y, so this would be j hat direction. And so this just gives you kind of the 2 simplest examples. Now, we can up the level of difficulty a little bit if we consider the case where instead of being on the line that's between them, let's go up a little bit. So suppose instead of looking, here, let's look like here. Now, if we do this, this magnetic field is the same orientation. It's going around in a circle like this. So, I can't draw a very good circle. There would be a magnetic field vector that would be pointing mostly up, but also a little bit to the left. You know that it has to be perpendicular to this R. So, and I could call, how about we call this one B1. Now, if we look at the magnetic field due to the other wire, same situation, the current's coming towards us. Now, in this case, it's going the other direction. So it's coming around like this, right? Just like the figure above. But now, so it's mostly vertical yet, in and down, but there would be a contribution that would be pointed in the negative x direction. So you can see that if you were to add these together, the y pieces would cancel. Because of symmetry. But the x is not going to cancel. So for this situation, we could calculate what this would be. So it's easy enough to calculate the magnitude. You know that the magnitude of this, well, of each contribution, so let me just call it B1, and we'll call this one B2. You know that this would just be mu naught I over 2 pi r, if r is that, hypotenuse there. And so, that's easy enough to compute, but adding up the vectors is where it gets a little bit more complicated. So what we would have to do is figure out the component of that that's in x. So we just want, this chunk. There would be 2 contributions. And what you can do is we would probably specify this angle here as being theta. And as long as we're on the, the center line of this, this wouldn't be so bad because this angle is going to be the same on both sides. And you can see that as you make that, let's call this y, how about? As you make that y displacement off the line between them smaller, that angle is going to shrink. So you can also identify that angle as being here or here. And as a result of that, you can see that the x piece that you're going to want would be the sine contribution. So if we went to find the total at this location, we're going to have a factor of 2 again because there's 2 contributions. We'd have our mu naught I over 2 pi r, i.e. just the magnitude without considering the direction. And then we would also pick up this factor of sine theta. They're both pointed in the same direction, so they're going to add. And we could express this sine theta in terms of y and r, for example. So if you look at this, you can see that sine theta would also equal y over r. So we could put those ingredients together, and we would see that this was, let me write it down below. 2 times mu naught I, 2 pi r times y over r for this case. And in this case, notice what happens if y gets small. So if y goes to 0, i.e. you move back to being on the center line, then this goes away. And that's the case that we had up here, the first one that we looked at. So that agrees with what we had. It's consistent with what we were talking about before. And then the other piece of information that we could add to this picture is the direction. So this is pointed in negative x. So this would have, negative I hat direction. Try and be a little more organized here. Okay, so those situations so far, we've been able to exploit symmetry. We've been able to, if we move off axis, it gets slightly more complicated, but it's still fairly simple because components cancel. And where we want to go next, though, is sort of the general case. And this gets more complicated. So the general case is, what if you have your wire here and your wire here again? But now instead of looking at a point that's on the line between them or off the line between them but still equidistant, you look at a point that's like here, and you want to know, what's the magnetic field look like here. So you can see that this is going to be a little bit more complicated because the magnitudes are not going to be the same because the distance is different. So again, if this is these currents are coming at you, you would have a contribution from this one that's pointed basically like this. So if this was I1 and I2, whereas the contribution from this one, let me put it in red just to distinguish here, would be much larger for the same current if I1 equals I2. And it would point, if it's also coming at you, it would point like this. It's got to be perpendicular to that, R. And so we have to figure out how to add together B1 and B2. We're going to have to be more careful with our angles. And that's kind of where this is headed. So there's a problem like this in your homework. So I'm going to show you an example that looks at this more complicated case. So the example that I want to consider, let me paste it in here. It's basically this. We have 2 long. So it's the same kind of setup, but the geometry looks like this. And so we need to find the magnitude and direction of the magnetic field at point P. And So you will notice there's a question like this in your homework, and they suggest to you that you use something called the law of cosines. And it's basically like you have to do a kind of tedious mathematical step first for us to be able to break this problem down. Because notice we don't know any of the angles, and it's not a convenient right triangle. So what you can do is use this. Let me paste it in here, what it is. It's a mathematical relationship between the sides in a triangle. And I would suggest to you, so actually let me annotate this a little bit, where this is A, this is C, and this is B, where these are angles. Okay, so capital A is angle, is across from side A, lowercase a. And these cosine expressions give you the relationship between the lengths of the sides and the angle. So it makes a lot of sense to like put this into your calculator or into the computer so that you can just compute these all at once. That's what I would recommend. I would not recommend like computing these by hand unless you compute them all and check them, you know, to check them against themselves to make sure you're confident. But you know, you can see how you would apply this, right? Like we could set up our triangle, um, you know, where suppose this is angle B or something, and A and C. And you could see, you know, we could, just to give you an idea, um, you just look at all these contributions. You know, and then you would evaluate this, and this would equal cosine A. And so if you wanted A, you'd take the inverse cosine of this, you know, all this stuff. And you can see you don't want to watch me do that, and it would be much better to like do it in the computer or figure out some way to compute this. So when I do that, I get that our angles in this triangle, our A is about 48 degrees, B is about 106 degrees, and C is about 26 degrees. So, and notice if you add these up, you get 180, like you expect for the interior angles of a triangle. So this is basically just sort of a preliminary step that you have to take care of in order to do the problem. So now that we have that information, let's qualitatively look at the problem and see how we're going to proceed. So we'll break this down just like we did those simpler cases. You know, now we know the angles. So maybe let's try and put that information in here a little bit. This is 100. Wow, it'll get kind of messy. So maybe I'll put it on the outside. This is 26 degrees. No, that's not 26 degrees. This is 48 degrees, 26 degrees, and you know the 105. All right, so let's put in our magnetic field vectors. For let's call them B1 and B2 again. For B1, so it's going to be on a line, you know, it's going to be perpendicular to this, you know, R that's connecting these points. So it would look kind of like this. Recall, you know, remember, do your right-hand rule. I'll try and draw this as neatly as I can. So B1 at that point would look kind of like that. It's got to be perpendicular here. And, you know, if you do the right-hand rule, your thumb would be pointing at you, and you can see it's going to, you know, in general, it's curling around the magnetic field like that. Okay. And then the contribution from B2, qualitatively, it's the same direction, right? It's going around the wire like this. And then at point P, you know that it's going to have to be perpendicular to this line. So it's going to look kind of like, let's see if I can draw this here, kind of like this. And, actually, let's try and make this slightly more accurate. Really, B1 is larger than B2 at this point because it's closer. So our vector should be longer to reflect that. Okay, so now we qualitatively have a picture of what we're going to do. We need to add those components together. Let's start cataloging the magnitude and the pieces that we'll need. So what is B1? Finding the magnitude is easy enough. We know that that will be mu naught times the current divided by 2 pi times our 0.06. And this is actually going to be, when we crunch the numbers here with the current of 35 amps, you find that this is 1.17 10 to the minus 4. B2 would be very similar. This current is the same, except the distance is different. It's 10 centimeters in this case. So, and we crunch those numbers, we find that this is 7 times 10 to the minus 5, smaller as we expect. And then let's look at the two pieces separately here. So for B1, we have basically this. If this is our, theta equals 48 degrees or whatever, we know that the magnetic field is off at an angle like this. You can see that. All right. I can draw it here. God. Okay. So if theta is here as well. And I think you can visualize this. Imagine theta getting really small. You can see how both of those angles would close. So what that means is that we can figure out which components are which. In other words, B1x, the x component, would be B1 times cosine theta. And B1, the y component of B, would be B1 sine theta. Okay. And we can kind of do the same thing with B2 here. So the cartoon for B2, oh man, if I can draw it. B2 is this smaller angle. So drawing them just one at a time. We know that, well here, let me actually put it in the other color too. This contribution, it's got to be perpendicular here. Try and draw it as similar as I can. So it looks something like this. And you can see that in this case, this angle is the same as actually this angle. So if this was phi or something, it's 26 degrees. Phi is also here. And you can kind of do the same mental thing. If you make, as phi goes to 0, you can see both of those angles would close. So the two contributions that you have are the x piece for B2. You can see it's pointed in the negative direction, so it would actually be, negative B2 cosine phi. And the y piece is positive, so that would be B2 sine phi. Okay, so now we have defined the x and y contributions from each magnetic field due to each wire. So then we would need to add them up. And now this starts to look more like what we're familiar with. If we want to find the sum of the x pieces, that would just be b1x plus b2x. And, that would look like u naught I over 2 pi times cosine plus the other piece. Or the numerical value. You could work with the numerical values. Oh, and this would of course be negative because it's pointed in the negative direction, or the negative x direction. In any case, we have all these ingredients. We could put this together and you'd find that this is 8 times 10 to the minus 5. One word of caution, actually, I would draw your attention to is with these questions where you have a lot of sort of steps, where you have intermediate calculations, be careful about rounding. It really is a bummer to work through a long question and then find that it doesn't like your answer because an intermediate step meant that something got rounded a little bit. So we have the x piece. Let's look at the y piece. We're almost there. So the pieces in y, we have, the contribution from B1, the contribution from B2. That'll look like u naught y over 2 pi times times our sine of phi. And we'll add to that the other piece. Oh, wait a second. This is phi. This is theta. Where, let's see, our theta was, this is 48 degrees. And this was our 26 degrees, etc. And if you compute this, you find this is 1.17 times 10 to the minus 4. Okay, so we have x and y pieces. So if we want to find the total magnitude, not a problem. We would take, the square root of the sum of the squares. And let's give ourselves a picture here so we can kind of figure out what it's going to look like. So they're both positive, so we know it's in the first quadrant. The x piece is actually smaller than the y piece, so it's, something like this. So we can use that to find that, helps us get oriented here. This is by and bx. So we can find the angle from the fact that tangent, let me call this let's call this alpha. It's because we have a lot of angles floating around. Tangent alpha would be the ratio of by over bx. So alpha would equal inverse tangent of, these two numbers. And when you compute that, you find that this is 82 degrees. Oh, and we didn't actually calculate the magnitude. When you compute this, you put, square root of these here. You find that the magnitude of B is 1.18 times 10 to the minus 4. So a fairly, involved question, but if you can solve something like this, this more general case, there's really a lot of problems that you could solve. And yeah, hopefully this helps with your homework.